So we're starting chapter 5. We'll finish off with 6.2, closely related to the material from chapter 5. But chapter 5, overview of chapter 5. In 5.1, we're going to look at approximating areas under a curve or a function. In 5.2, we'll look at the definite integral. We have seen from 4.9, we've seen what we call a definite integral, or sorry, indefinite integral, 4.9. So from the 4.9, the indefinite integral was an antiderivative of some function with respect to a variable. The definite integral takes on a different context. In 5.3, we'll look at the fundamental theorem of calculus. And so it's not really until 5.3 where we can develop a shortcut method to find the area under a curve. So that's where the fundamental theorem of calculus comes in. 5.4, we look at the, it's called working with integrals, but we look at the average value. Of a function. There might be another component there, but that's the biggest thing we look at in 5.4. Can't quite remember. 5.5, we look at substitution. Substitution rule for definite integrals. And then finally, in 6.2, we're looking at the area between curves. So all of chapter 5, ultimately we're looking at the area between the function and the x-axis. And then in 6.2, we look at the area between two functions. So that's what we're going to be doing for the remainder of the semester. So in 5.1, then we're looking at approximating areas under a curve. And so our chapter 3, chapter 4 stuff was kind of the left branch of this tree where we were given a function, compute the derivative, interpret that as the slope of a tangent line or the instantaneous rate of change as like a physical context. So we also had the instantaneous rate of change. And chapter 5 is really we're developing ideas of interpretations of what an antiderivative does for us. So here's a reminder of displacement on a specific time interval. So displacement was just the change in the position where you ended minus where you started. All right, so just kind of a simplistic example to illustrate this idea. We've got a velocity function that's constant at 60 miles per hour for the first 2 hours. And we want to know what is the displacement, the change in position in the first 2 hours. So maybe we should say from 0 to 2. So what is the change in position there, the displacement?
0.
0, okay. Anybody have any other ideas? 0 seem reasonable. You traveled 60 miles per hour for 2 hours. So that's the problem, right? We don't have a position function. We can say this is the position I started with and this is the position I ended with. We're given a velocity function, which we know is related to the position function.
Maybe he stayed constant at a 0. He started off with the constant at 0 and took 4.
Yeah. So we start out at time equals 0. We're traveling 60 miles an hour when somebody starts measuring our speed, and we keep traveling 60 miles an hour for 2 hours. So how far did we go?
120 miles.
Yeah, 120 miles is the displacement. Is the change in position. We don't have a position function, but we know that we've gone 60 miles per hour for 2 hours. So yeah, we could, since we know that the antiderivative of the velocity function with respect to t is equal to the position function, right? We could say, well, our position function then is
60t plus c.
60t plus c. So that the problem there is we don't know the initial position. Where did we start at?
0.
And I guess you could say you started at 0, right? But then there's other options. We could have started, 50 miles down the road. Huh?
The interval.
The interval? Well, right, but the interval doesn't really tell us where we started. It just says from a time equals 0 to time equals to 2. It has nothing to do. We would need to know s of 0 to know the initial position. But it does kind of build in with this idea of what we're talking about here, the displacement. If we knew this sort of position function and its constant or its initial position, the equivalent way to come up with the displacement here is to just note that we've traveled the length of this, if you will, 2 hours, and the height of this is 60. And to get the displacement, that's what we did. We just multiplied 60 by 2. The, I guess, geometric or the visual interpretation of the displacement here is simply the length times the width, or the height times the length, the area of this rectangle. So if I look at this rectangle and I compute the area is the displacement. So it might give us a little bit of insight into, how the antiderivative plays into sort of a physical interpretation. If we look at the antiderivative of some function, that's what we're doing is we're computing the area between some time and the function itself. So that's also, we'll just state for now, that's the area. under the velocity. Bound by the t-axis. So I mean, it seems like a perfectly legitimate connection to make for a relatively straightforward velocity function. The issue that arises, though, is what if we had a velocity function that wasn't constant? So what if our velocity function looked like, you know, something like this over some time interval? Yeah.
That's probably not the average of that.
So the average is the average value of the function, you mean? So the average value of the function is closely related. Yeah, so it's closely related, but it's not identical to the area. Yeah. So then, you know, if I wanted to know the displacement here from 0 to 2, let's say 2 is here. The displacement on 0, 2 for this thing, it's equivalent to the previous example, but our function is a little bit more complex. The displacement still is the area, but then that begs the question, how do we find this area? If it's not some nice geometric figure that we have a formula to take the area, like a circle, a rectangle, etc., then how would we compute an area such as that? And that's really the heart of chapter 5, is computing areas such as that. So the idea to compute that area, does anyone have any ideas, or maybe you've seen it before? Yeah, so the idea is just a pretty straightforward approach, kind of based on the last example. If I had a bunch of rectangles in here, or let's just say a few rectangles in here, then I can compute the area of each individual rectangle and say that the area of all of those rectangles is pretty close to the area underneath that curve.
I'm sorry, but the spaces that are like come out of the actual line, is that doesn't that make our area inaccurate?
Yeah, it makes sure, it definitely makes the area inaccurate. So this would, if we said the area of this rectangle plus this one plus this one plus this one, the area is going to over-approximate the actual area. But that's the basic idea. So, you know, what we're doing here is we're dividing the interval that we're concerned with, 0 to 2, into subintervals. Computing the area of each rectangle and adding those up. To get an approximation to the actual area. So that's the basic idea behind a lot of what we do in chapter 5. As we progress through this chapter, or this section rather, it's all about approximating, and then we start to gain some insight on how to make that area exact. And then in 5.2 is where we start looking at methods to compute the exact area. Okay. So do y'all have any questions on this idea? Honestly, it's pretty tedious just because of the notation, but we do end up moving away from this. It's kind of like with the derivatives and using the definition of a derivative. That was kind of a pain to compute the limit as h went to 0 on the, what do we call it, the difference quotient. So and then we looked at shortcuts. It's much the same in chapter 5. So we look at this really long and tedious method, and then we make these certain connections, and then we start looking at shortcut methods. So our example is we're going to use that idea to compute the displacement on the velocity function t squared from 0 to 8. And we're going to approximate the displacement by partitioning the interval 0, 8 into a certain number of subintervals, or a certain number of rectangles. So you can think of the number of subintervals as the number of rectangles. All right, so for the first computation, let's look at, so this is part A. We'll call it n equals to 2 subintervals. In other words, we're approximating the area on t squared from 0 to 8 using 2 rectangles. So right now we'll just kind of draw it out, and then we'll look at the specific notation that allows us to sort of bypass drawing pictures. Okay, so there's the velocity t squared, and we're going from 0 to 8. And we're going to split 0 to 8 up into 2 different rectangles. So rectangle 1 would go from where to where?
0 to 4.
0 to 4. And then rectangle 2 would go from 4 to 8. So at this point, you've got to specify you've got to use a certain point in each rectangle to evaluate the rectangle's height, which is why we said use the midpoint for the height of the rectangles. Because notice, I mean, arbitrarily I could draw this rectangle here, and I could draw this rectangle here. I could draw this rectangle here, and this rectangle there, right? Or, you know, there's I guess, a multitude of ways to do that. I could say, well, my first rectangle, I wanted to have this height. My second rectangle, this height right here. All right, so once we specify, use the midpoint for each, then we know exactly how we're going to construct the height of each rectangle. So the midpoint between 0 and 4 would be 2. So that's the t value that we're using to determine the height of the rectangle. So we're going to just go up to the function and generate that rectangle. And the second interval from 4 to 8, midpoint there is 6. We're going to use that t value up to the function to give us the height of that rectangle. Primarily in this section, we're either working with a midpoint, the right endpoint, or the left endpoint of each rectangle to determine the height. So the area under this curve is approximately the area of, we'll just say for now, rectangle 1 plus the area of rectangle 2. So what's the area of rectangle number 1? 8, what do y'all think? What's the length of the first rectangle?
4.
What's the length? 4? Okay, so we go from 0 to 4, the length of that rectangle is 4. What's the height of that rectangle? It's also 4. How are we getting the height? The function, right. The function determines the height. The function evaluated at 2 determined the height of that rectangle. So let me just draw this rectangle here. So the length was 4, but the height is equal to v at 2, which was our midpoint. Is everybody okay with that? So for all of these, the height of every one of your rectangles in any one of these examples we look at is always determined by the function. So the function was just the squaring function. So 2 squared gave us a height of 4. And the similar thing for the second rectangle, we've got this rectangle. Again, the base is 4. The height of the second rectangle is what? Second height is 36 because that comes from the function t squared evaluated at 6. That makes sense? Do y'all have any questions on that? All right. So that's approximately that. It's approximately base times height for that rectangle plus base times height for this rectangle. So what do we get for the approximate area? Let me just note here that the actual area for this particular graph the actual or the exact area is 170.6 repeating. So 170.6 is the actual area. We're coming up with an area of about 160. Using only 2 rectangles. Is everybody all right with that? Are there any questions? Okay, so maybe let's do for part B. For part B, the number of rectangles equals to 4. So what do you think is going to happen with this approximation?
It's going to get closer to the exact.
Right, it's going to get better because we're using more rectangles. So this time we're using 4 rectangles, which means we're dividing 0,8 into 4 different pieces. How long or the length of each rectangle now would be what? We've got to fit 4 rectangles from 0 to 8. They're all going to have a length of what? 2. So the first rectangle goes from 0 to 2. Then we go from 2 to 4. Then we go from 4 to 6. And then 6 to 8. So that's what we referred to earlier. That's forming a partition of the interval 0, 8. And again, we're using the midpoint of each subinterval to determine the height of the rectangle. So Yeah, so here the height is going to be determined by the function at 1. Second subinterval, function evaluated at 3. Third is the function evaluated at 5. And the fourth, the function evaluated at 7. So those are the heights of each rectangle given there. All right, and we'll just write this out. The area is approximately area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3 plus the area of rectangle 4. What's the height of the first rectangle?
2.
Length is 2, height is 1, that's f of 1. What's the height of the second rectangle? 3 squared. The height of the third rectangle? 5 squared. And the height of the fourth rectangle? 49. 7 squared. And notice that's sort of arbitrary, right? We could have said, well, let me use the left endpoint to evaluate the height, or the right endpoint to evaluate the height, or any value in between 1 and 2 to evaluate the height. So we've got the area of rectangle 1 is the base. Notice the base of the rectangles are always the same. We're keeping those uniform. So here it's 2. So we have the base times the height. Let me just write this out so we can see this. The base times the height. Area of rectangle 2, base times the height. Area of rectangle 3, base times height. Area of rectangle 4, base times height. Yeah, well, v is the squaring function. So this v of 1 is 1 squared, v of 3 is 3 squared, and so forth. All right, so each rectangle's area added up. We have 1 plus 9 plus 25 plus 49 times 2. So that's giving us what?
168.
168. So we went from 2 rectangles, an area of 160. 4 rectangles gave us an area of 168. The actual area is 170.6. So, you know, hopefully it's intuitive that as we add more and more rectangles, that area is going to get better. The approximation of the area, rather, is going to get better and better. Do y'all have any questions on this idea? All right. So here's a table if we were just to keep going. Here are the 2 that we computed. So we did these 2. If we were to do 8, 16, 32, and 64, then our approximations are over here. So here's the length of each subinterval or rectangle. The length of each, the length of the base of each rectangle as we increase the subintervals and then their appropriate approximation. And this is a figure with 64 rectangles. So now what we see is that sort of how much we're over approximating by each rectangle is decreasing, right? It's getting smaller and smaller. The error is getting smaller and smaller. So with that in mind, how would we come up with an exact area under t squared from 0 to 8?
Making it infinite.
Right. So the exact area, the number of subintervals or rectangles needs to be infinite. I mean, as a thing, that's not possible. You can't put infinitely many rectangles in that region. But through the lens of calculus, we can do that by doing what? What kind of process does this become? A limiting process, right? So the number of rectangles is n. So we just compute the limit as the number of rectangles n approach infinity on something, and we'll have to talk about what that is. We've already seen what it is, but we have to make it a little bit more precise. So that's where the limit comes in also in giving us areas under curves. Are there any questions at this point? Okay, so this sort of figure we're going to look at is kind of helping us come up with this notation that we're going to see in the definition. Definition of the regular partition and of the area itself, the approximate area. So the idea is a little bit more technical. We have a function from A to B, and we're going to split that up into some number of partitions or some number of rectangles. We're going to call the A our x sub 0, and B we're going to say is x sub n. So in our previous example, x sub 0 would have been equal to 0, and x sub n would have been equal to 8. We would have gone out to 4, because we used 4 rectangles. So again, when you see this n, you just think of the number of rectangles that we're using. And so the first rectangle goes from x sub 0 to x sub 1. Next rectangle from x sub 1 to x sub 2. The last rectangle is from x sub n minus 1 to x sub n. But each one of the endpoints of the rectangle we're going to call a grid point. So the endpoint of each rectangle is a grid point. And then so we have these varying subintervals, x sub 0 to 1, x sub 1 to 2, and so forth. This is our first subinterval or our first rectangle. This is our second rectangle. And this is our nth rectangle, whether it's the 4th or the 32nd or the 64th rectangle. That's where we're ending. Okay. And for each subinterval, x sub 0 to x sub 1, we're going to pick an x value. We're going to call it x star, so we don't get it confused with the endpoints. So this x star sub 1 just indicates that this is the x value that we're using to get the height of that rectangle. In the second rectangle, to get its height, I would use x star sub 2. In the third, I would use x star sub 3. All of those x stars are the x value that gives us the height of the rectangle itself. So that's the idea. The x star sub 1 is the x value in the first subinterval or the first rectangle that gives us the height of the rectangle. In other words, the height of the first rectangle is the function evaluated at x star sub 1. The height of the nth rectangle, is the function evaluated at x star sub n. The height of the second rectangle is the function evaluated at x star sub 2, and so on and so on. So when we've got a little subscript on x, that's just indicating the endpoints of the rectangles. The x stars are the values in that interval that give us the height of the rectangle. So the definition of a regular partition, we've got a closed interval from a to b, from 0 to 8, whatever. And it contains these specific subintervals of equal length. So that's really the prevalent idea throughout all of this stuff, is that we're going to keep those equal length. It doesn't matter if their lengths vary, but just for a simpler computation, we're keeping all of the rectangles equal length. Okay. The length of each rectangle is defined as delta x. Delta x, the length of each rectangle. And the length of each rectangle is the length of your entire interval divided by how many rectangles you're putting in that interval. So like that previous example, when we had the interval from 0 to 8 with n equal to 4, we said the rectangle's lengths were all 2. Because delta x is the total length of your interval divided by how many rectangles you're putting in that. So the length of all of those were 2. I mean, and that was a little bit more straightforward because we're not using that many rectangles, and we were able just to draw it out. The idea is when we're just given some random function on an interval, to not have to draw it out and kind of think about, because what if we use like 50 intervals? Would you want to draw 50 rectangles just to see where everything's at? All right, so all rectangles have equal length, delta x. A is x sub 0, b is x sub n. The endpoints, x sub 0, 1, 2, 3, are the grid points, and they're creating what we're defining as a regular partition. So the kth grid point is given by this formula. So the kth endpoint of the rectangle, x sub k, is a, which is this value here, where your interval starts, right? Because this is from a to b. So it's a plus k times delta x, which is the length of each rectangle. And then k gets indexed 0, 1, 2, 3, 4, all the way up to however many rectangles you're using, which is n. And then, so what we had was, let's go back to this example. That we computed already, just to see how this works. On 0, 8. Oops. 0, 8. With 4 rectangles. So maybe our instructions could be here to list the grid points. And each subinterval. And we've already done that by drawing a picture, but hopefully this leads us into a technique where we don't have to draw the picture. All right, first, we need to find delta x, which is b minus a over n. So our closed interval 0 to 8, that's our A and B. So A is 0, B is 8, and N is given to us as 4. So we computed that just a minute ago. 8 minus 0 over 4 gives us 2. So that's our delta x. In other words, the length of each rectangle is 2 units long. And since we're listing all of the grid points, we're going to use this formula for all grid points. K equals 0, 1, 2, 3, 4. And that's where we're stopping. Because we stop at n, and our n is equal to 4. I guess we'll say next. Find the grid points. X sub k is a plus k delta x, for k equals 0, 1, 2, 3, and 4. So you can't find the grid points until you know the length of each rectangle, because delta x is a necessary part of that formula. All right. So first grid point happens when k is equal to 0. So when k is equal to 0, we have x sub k, which is 0, equals to a. What was our a?
0.
A is 0 plus k times delta x. Our delta x was 2. And notice this k right here, let me do this. That k in the formula matches the k that's on the subscript of x. So this, don't get these two zeros confused. This 0 that's multiplying 2 is just based off of the subscript on x. The first 0 was from a itself. All right, so that tells us that x sub 0 is 0 plus 0, 0. So that's our first grid point. Our second grid point comes from a k value of 1. So we have x sub 1 is equal to a, which is 0, plus k times delta x. So that tells us our next grid point is 0 plus 1 times 2. So x sub 1 is equal to 2. And that's fitting in with what we had when we took the squared function from 0 to 8, and we said divide that into 4 rectangles. This first rectangle was from 0 to 2, right? And then the next one was from 2 to 4, so forth. So those are the numbers that we're going to get out of doing all of this. It's just a bit more, I don't know, maybe initially it seems tedious, especially when you have a small subinterval and a small number of rectangles you're putting in. But if you've got a really large subinterval that you're putting a lot of rectangles in, it's probably more efficient. And then you can start to see how these things develop. Next k value is k equals to 2, so we're going to have x sub 2 is a plus k times delta x. Delta x is still 2. So that gives us x sub 2 equals 4. Next grid point, when k equals 3, we have x sub 3 equals to a plus k delta x. So x sub 3 is 6. So all of these grid points, we're just taking a k value and multiplying it by 2, because that's our delta x. So when k equals 4, we've got x sub 4 is a plus k delta x. X sub 4, which is 8. So those are all of our grid points, 0, 2, 4, 6, and 8. Which forms the partition (0 to 2), 2 to 4, 4 to 6, and 6 to 8. And if you'll remember, that's exactly how this diagram was split up. So now if we said use the midpoint, then we just take the first subinterval, 0 to 2. What's the midpoint? It's 1. That's the function's height, evaluated at 1. The next 2 to 4, midpoint is 3. Plug that into the function to get the rectangle's height. Midpoint's 5. Into the function gives us the height, so forth. We'll also work with the left and the right points here. So, we could use, if we use the left, then we would evaluate the function at 0 to get its height here, the function at 2 to get its height, the function at 4, and the function at 6. And if we use the right endpoint, then we would use 2, 4, 6, and 8 to get those rectangles' heights. So do y'all have any questions on that? The notation's a bit cumbersome, but that's kind of how these are going to work. So just for time, do y'all have that? Is that in y'all's notes?
Yeah.
Okay, so this is another example on an interval from 1 to 9, partitioned into 4 subintervals, which is telling us that n equals 4. What is delta x and what are the grid points? So delta x is b minus a over n, which gives us 2. And then the grid points are computed the same way we computed the previous grid points, except for now these look a little bit different. Let me do this. So we can see how. So that's just another example. We're getting the grid points of 1, 3, 5, 7, and 9, which then form the partition 1 to 3, 3 to 5, 5 to 7, 7 to 9. And so, visualize that interval from 1 to 9 now being broke up by this. This is actually a rectangle here. So this thing's representing, all of these are representing the length of a rectangle. And then, the height of each rectangle is going to be determined by the function. But all of these are representing rectangles. The base of them anyways. Alright, so maybe you can look over that if you're going to feel shaky on what we're doing. So the definition that we see below is generated by the fact that if we can approximate an area by summing all of those rectangles, And let's just kind of break this up a little bit. The area of the first rectangle was the length, which we're going to refer to now as delta x. Well, let's kind of one step removed here. So it's the length of the first rectangle times the height of the first rectangle, plus the length of the second rectangle times the height of the second rectangle, and so forth. Okay. But the length was given by delta x in all of these, and the height is given by the function evaluated at some x value. Again, we're going to call that x value x star, and since it's corresponding to the first rectangle, it's x star sub 1. And we have plus delta x, the length of the second rectangle, times the height of the second rectangle, f evaluated at x star sub 2, since it's in the second rectangle, all the way up to delta x times f evaluated at x star sub n. So that's really a more formal way to think about the area of rectangle 1 plus the area of rectangle 2, et cetera, et cetera. Okay. And then so we see that in the definition. When we define a Riemann sum, this is a mathematician, I guess, Riemann. I'm not sure. Maybe. I don't know that I've seen it. Huh? Oh, Russell Crowe. No, that was A Beautiful Mind. That was John Nash. Yeah.
He was like.
This guy's super old.
And he goes to Milton Gale, and he like does like some fancy formula. That sounds like his name.
I don't know. I have to check it out. I've never seen it. I've never seen a movie about
It's
him.
really good.
I'll check it out. So that's the definition. That's how we're going to refer to as the approximation of the area now. We're gonna say it's a Riemann sum. So notice the area is approximately this. That's just what we said here. Delta x times x star sub 1. That's a length times a height, plus another length times another height, plus another length times another height, et cetera, et cetera. And I guess sort of to make the notation a bit more confusing, notice now this x star sub k is also indexed by k, but this k is ranging from from 1 to n, where the k that was on the actual endpoints or the grid points ranged from 0 to n. So this k is starting at 1 just because we're saying that's the x value in the first rectangle that we're evaluating the height. The x value in the second rectangle, the x value in the third, and the x value in the nth rectangle. We can't have a 0th rectangle. I mean, I guess we could, but it would be weird. So the midpoint here we used in our previous examples to compute the approximate area. So we've used that in our previous example. But then we get a sense of these other two, the left Riemann sum and the right Riemann sum. So the left Riemann sum simply says to evaluate the height of each rectangle, you take the left grid point and use that as the function value, the input into the function. The right Riemann sum, we use the right grid point. So notice the right Riemann sum, the left Riemann sum, the midpoint Riemann sum, they're all talking about this x star. And that x star is always the thing that's plugged into the function to give you the height. So what changes by that left, right, midpoint is just what we evaluate the function at. The delta x stays the same. Do y'all have any questions about this? It's not the prettiest looking stuff. guess I won't hold you responsible for knowing this definition. I think having an idea of what this definition is saying is much more important than remembering where all the little things go. And so we'll use that as our next example. F of x is the sine of x, and we're looking on the interval from 0 to pi over 2. We want to approximate the area of the region using right, left, and midpoint Riemann sums using 6 subintervals. So if you want, you can draw this function out, the sine from 0 to pi over 2, and then partition that into 6 subintervals. Determine what this point is, what this one is, what this one is, what this one is, what this one is, and then use the left, right. So you can draw a picture out if you want, if that makes sense, but we're going to just use sort of the definition of all this stuff so we don't have to draw a picture. And really what we're after is the grid points. So we need the grid points. So we need the endpoints or the grid points of each rectangle. And finding the grid points, as we've seen, it gives us what the partition is, right? So we need the grid points for each rectangle, subsequently gives us the partition. All of our grid points are x sub whatever, x sub k, which is defined as a plus k times delta x. K ranges from 0 to where? Where would k stop at in this example? Well, the last rectangle would stop at pi over 2, but the k, as far as indexing it from 0 to...
6.
Yeah. So remember, k ranges from 0 to n, and then we said we're going to use 6 subintervals, so that tells us n is equal to 6. All right, so in order to do that, we need the endpoints or the grid points. So our first step, looking at this formula, we're given a lot of this stuff, but we need to find delta x. Delta x is b minus a over n. So what's our a and what's our b? Okay, so the interval that we're given is a and b. So that's pi over 2 minus 0 divided by the number of subintervals, which is 6. Yeah, pi over 12. So we've got our delta x. That's going to enable us to find the endpoints here for these rectangles. So next, find the grid points. So first grid point comes from k equal to 0. And so x sub 0, x sub k is a, which is 0, plus k times delta x. Remember, x sub 0 is always the starting value of the closed interval you're given, so those should always coincide. So you can use that to check as well. The k sub 6 should also equal the last value of your, or the end point of your closed interval. So our x sub 6 should be equal to pi over 2, x sub 0 should equal 0. Next grid point comes from when k equals 1, so that's x sub 1 equals to a plus k times delta x, 1 times delta x. That's pi over 12 for the next grid point. What would our third grid point be? When k equals 2. Yeah, k equals 2, we have x sub 2 equals to a plus k times delta x. So we've got 2 pi over 12, x sub 2 is pi over 6. Fourth grid point when k is equal to 3. We have x sub 3 is 0 plus, yeah, k times delta x, 3 times pi over 12. Oh, sorry, pi over 2. Wait, what was our delta x was pi over 12? So 3 pi over 12, 1 pi over 4. And then once you do maybe one or two of these, you can see the pattern. The subscript on x is just multiplied here anyways. With this example, the subscript is just multiplied by pi over 12. So the next value when k is 4 times pi over 12, 5 times pi over 12, and then 6 times pi over 12. But so we'll just keep going. K equals 4, x sub 4 is 0 plus 4 times pi over 12. So x sub 4 is pi over 3. Let me get this done here. And our last grid point when k, or no, next to last when k equals 5, x sub 5 is 5 times delta x. So 5 pi over 12. And our last grid point when k equals 6, x sub 6 is 6 times pi over 12, which is pi over 2. So these are all of our grid points. So maybe you find it faster with this example to draw it out. If you want to draw it out, that's fine. There's nothing wrong with that. So our partition then becomes first rectangle from 0 to pi over 12. Then we go from pi over 12 to pi over 6, and pi over 6 to pi over 4. Pi over 4 to, let's see, pi over 3. Pi over 3 to 5 pi over 12, and then 5 pi over 12 to pi over 2. Again, those are the rectangles. This is rectangle 1, 2, 3, 4, 5, 6. So whether we're looking at the left Riemann sum, the right Riemann sum, or the midpoint Riemann sum, the way that interval is partitioned does not change. So you've got this partition for all three of your Riemann sums. Do y'all have any questions on what we've done? All right. So then we're going to do, what was it? Part A was the right Riemann sum. I'll just abbreviate Riemann sum. Partition found previous, and all it means to use the right Riemann sum is for each of those rectangles to use the right endpoint. So we're going to use the right endpoint here, the right, and so all of those values are going into the function to get the rectangle's height. So the area then is approximately, like we said, it's delta x. You know, delta x is attached to all of the f's, right? So you could leave the delta x out and multiply just the function evaluated at pi over 12. I can fit all of this in here. Plus the function evaluated at pi over 6. Plus the function evaluated at pi over 4, plus the function evaluated at pi over 3, plus the function evaluated at 5 pi over 12, and plus the function evaluated at pi over 2. Is everybody all right with that? Do y'all have any questions at all at this point?
My math left was long.
Yeah. This homework is tedious. All right, delta x we found to be what, pi over 12? So we'll call that our pi over 12. Our function was what? Sine. So we've got to plug in, we've got to evaluate sine of pi over 12, pi over 6, pi over 4, pi over 3, etc. to get that area. Again, what we have in brackets is the height of each rectangle. Is everybody with us? You don't have any questions at all? What we're doing here? All right, so type in your calculator. You get 1.125. I thought Clear Checks had a picture of that. They don't. Oh. So are there any questions on what we've done there? So that's the approximate area under the sine function from 0 to pi over 2 in the x-axis using 6 subintervals. So just to give a visual of that. That's, if we were to draw it out, that's what we're computing. So here's our partition from 0 to pi over 12. We said use the right endpoint to evaluate the function's height. So f of pi over 12, sine of pi over 12. Next one, we went from pi over 12 to pi over 6, right endpoint to evaluate the rectangle's height, f sine of pi over 6, and so forth. That's giving us the height of each rectangle. So maybe the notation in the work is a bit cumbersome, but I hope the idea of what we're doing here is straightforward at this point. Do y'all have any other questions about what we're doing? All right, we'll take a break and then look at the left Riemann sum and the midpoint. But since we've got the grid points, most of the work, I guess, is done other than just punching it into your calculator. All right, we'll continue with the left and midpoint Riemann sums. This idea of, a two-dimensional area, kind of putting in rectangles, does extend into higher dimensions. So I guess if you move on to Calc 3, you'll see how volumes are computed in the same way. So you take some three-dimensional object, like a sphere, and sort of on the X, Y, and Z axis here, we kind of form these, instead of finding an area, we're finding a volume. So you form all of these squares. You find the area of the square, and then the height of the square, or I guess prism. If I can draw this very well. And so that you're computing all of these tiny little volumes that are inside this. It's a terrible drawing, but the idea does extend to higher dimensions. And then that you can compute volumes in the same way, I guess a hypervolume, whatever. All right, left Riemann sum. So we're just going to use the left endpoints into the inside the function to determine the height of each rectangle. So here the area is our delta x, the length of each rectangle, times the height of each rectangle.
Wait, why is it?
Sorry, what?
Sorry, I was thinking
You're thinking of which ones?
I was thinking f of 0 instead of sine of 0.
Oh, okay, yeah, f of 0.
I
Here-
realized.
Yeah, that's accurate. All right. So you can see, that just shifts it over from where we were previously with the right Riemann sum. And then this area is approximately 0.863. So again, once you have the grid points, I guess it's still a little bit tedious to plug in all those function values, but at least you have your bearings on the problem once you have your grid points. And if we were to look at this visually, we're looking at this. So the first rectangle, the height is found here, which is 0. And the left Riemann sums for the heights of these. Or the left endpoint, rather. So we see visually and numerically that our right Riemann sum over approximates the area because we've got all these chunks above the curve. The left Riemann sum under approximates the area. And then so essentially to take the average of those two is to look at the midpoint Riemann sum. Which would be part C. And so now we're just going to look for the or determine the midpoint of each. So the midpoint between 0 and pi over 12 is what? Yeah, pi over 24. And between pi over 12 and pi over 6, pi over 8. And so on and so on. So just for time reasons, it's going to work out the same way or be constructed in a similar way. So for the midpoint, you should get an area of approximately 1.003. And I guess maybe for an extra thing, so we can kind of have a frame of reference for part D, the exact area is 1. Area equals 1. So then we can kind of compare our left, right Riemann, midpoint Riemann sums to the actual area. You know, all three of them were relatively close, considering we're only using 6 rectangles.
Could you just not add the two dimensions? Left and right?
Yeah, so what happens when we add the right Riemann sum
Gives you 0.9
and the, so you did that already?
Yeah.
So kind of a separate computation. If we took the right Riemann sum plus the left Riemann sum, and then we divide that by 2 to average. And what did you get, Joel?
0.994.
0.994. So it's not exactly what we got with the midpoint Riemann sum, but yet it's also a good approximation of the actual area. Like I said, it's not until 5.2, the next section, where we look at computing an exact area the hard way. And then after sort of towards the end of 5.3, we look at a shortcut way to compute the area exactly. Do y'all have any questions on that example?
Is there gonna be a reason why we would do the left or right?
As far as the working definition of the exact area, we'll use the right Riemann sum just because we'll see its formula is a little bit simpler. But ultimately, where we're going as filling up the region with infinitely many rectangles, it's not going to matter whether you do the left, right, midpoint, or some other type of Riemann sum, because it's all going to come out as exact anyways. But as a working definition, we're using the right Riemann sum because it is a simpler thing to use. So the summation notation is going to allow us to represent sums in a more compact way that we will use moving forward. So sigma notation, sigma just represents a sum. So sigma notation looks like this. You've got a sigma, a starting value, an ending value, and some expression. Each time and the starting and ending values are always whole numbers. So these are counting numbers. Zero, 1, 2, 3, 4, 5, sometimes called the natural numbers. And we'll look at a few examples just to kind of see how this works out. So example 1, instead of writing like 1 plus 2 plus 3 plus 4 plus 5 plus 6, we can write instead the sum from, we'll call our index k because that's the index on the Riemann sum. K equals 1 to 6 of k. So we start off with k equals 1, plug that in, get this 1, and then when the index change or the counting number changes to 2, we have an addition in between is what the sigma is telling us. So here's k equals 1, k equals 2, k equals 3, 4, 5, and 6, and we stop at 6. What if we wrote the sum from 2 to plus 3 plus 4 plus 5 all the way out to 100? What would the sigma notation for that look like?
Be sigma from k equals 2 on top of 100 of k.
Yeah, so k equals 2, go all the way out to 100, and we're just summing those particular numbers. No, I'm running out of room. So how about the sum, looking at this the other way, sum k equals 0 to 4. Our expression is k squared plus k. What would that sum look like? So first value is when k is 0, and we plug that into the expression 0 squared plus 0. K is now 1, we're going to add, so 1 squared plus 1. Then k is 2, 2 squared plus 2. K is 3, 3 squared plus 3. And then end at k is 4, 4 squared plus 4. And the reason we're using this notation, of course, is because we don't want to keep writing out delta x times f x star sub 1 plus delta x f of x star sub 2. So that's basically our condensed version. We're going to take all of that stuff for the Riemann sum and condense it into sigma notation. A few properties are here. So when we're dealing with some constant times an expression involving k, the constant can come out. Because think about this sum as a function of k. So if it doesn't involve a k, we can pull it out of the summation. This one says if we have two expressions involving k, then we can sort of distribute that summation across sums and differences.
Delta x is, that'd be the constant.
Yeah, right. So in reference to property number 1 and what we're looking at, delta x is a constant. So the delta x can be pulled out of the Riemann sum, like we did when we computed the sign of all of those values. An example of this, based on the previous one, if we had the sum from k equals 0 to 4 of k squared plus k, we can look at that as the sum from 0 to 4 of k squared plus the sum from 0 to 4 of k. And so these properties allow us to sort of condense the computations for our Riemann sums as well. Do y'all have any questions on this notation? Okay. So the formulas for certain powers of k. We've got, the first one here is the sum of a constant, so we'll call this one number 1. And look at a specific example. So if I said the sum from k equals 1 to 50 of, I don't know, 10. So what this sum is actually representing is when k is 1, your value is 10 plus 10 plus 10 plus 10 plus 10, 50 times, right? So it's 10 plus 10, 50 times. So we see why that formula is the way it is. I'm just taking 50 times 10, or the upper limit times the constant. So these are just very efficient, quick ways to compute these sums. And notice that the sums on k here turn into an expression involving n, where n is your ending point. So as long as we're starting with 1, these things are valid, and it's perfectly fitting, because when we look at, again, the definition of the Riemann sum was delta x times x star sub 1, x star sub 2, right? That k value for the function, the thing we're plugging in the function, always starts at 1. So we've got them sort of in line or in preparation for those particular things. Let's call this one the sum from k equals 1 to n of just k, number 2. So if I had to sum k equals 1 to 100 of k, which of course that's 1 plus 2 plus 3 all the way out to 100. The formula for that type of sum is n times n plus 1. And again, n is just where you're stopping. So here n is equal to 100. This formula becomes 100 times 100 plus 1, all divided by 2. And we can kind of reason through this one too. The idea with this sum, so the story goes like a 14-year-old mathematician was asked this in class, and he was able to come up with the answer in like a minute or less. And the teacher was like, "Oh, how did you do that?" And so his method was to take this 100, add it to this 1, so you've got 101, and then we take 99 plus 2, which is also 101, 98 plus 3, 101, and we keep doing that till all of those pairs are accounted for. Each time the sum is 101. There's 100 of these things here, but we've paired them up, or we've double counted, so we end up dividing by 2. Okay, so when we sum the first n integers, the sum is always n plus 1 over 2. Summing the first integer squared, n plus 1, 2n plus 1 over 6. We'll call that number 3. So for instance, if we had to sum k equals 1 to 50, so we're summing the first 50 integers, the square of the first 50 integers. So 1 squared plus 2 squared, etc. The formula is n, which is where we're ending at, so it's 50 times n plus 1 times 2n plus 1, so 50 times 2, 100 plus 1, all over 6. And I didn't actually compute these values, but much more efficient than typing out 1 squared plus 2 squared plus 3 squared plus 4 squared. And then the fourth one is for the sum of the first integers, sum of the first n integers cubed. So notice that formula is the one above it, just squared. So n squared, n plus 1 squared over 2 squared. We'll call that one 4. So 1 to 20 out of all of the cubes. So that would be equal to n squared, so 20 squared, times n plus 1 squared, all over 4. So that's how those things are working. does limit us to what sort of functions we can look at as far as the Riemann sum goes, because it's just limiting us to like a function that involves x plus a constant, x squared, a constant, x squared, x constants, x cubed. Because if we had like x to the fourth or x to the fifth, we don't have a formula to sum those types of things. I mean, there are formulas, I believe, for some of them, but you know, if we had the sine function, there's not a formula for the sum of the sine of case or sum of sine k squared or anything like that. So this, by hand anyways, this is severely limiting us to what sort of Riemann sums we can compute by hand. But it does take care of, you know, up to, I guess, the cubic polynomials. Do y'all have any questions on those? You should eventually know these. I'm gonna pass out a formula later that sort of eliminates. This is a longer way to compute Riemann sums. The formula that I've printed out isn't actually in your textbook. It comes from another textbook, and it's much more efficient to compute Riemann sums by hand. But one way or the other, you should remember this or the other formula for these types of sums. And so with sigma notation, then we just go back to our Riemann sum, and instead of writing delta x times f1 plus et cetera, we're just modifying the definition now to have sigma notation in it. So that's our Riemann sum as previously stated, just with sigma notation. So think about k representing the the x value in the first rectangle, and then we move on to the second rectangle and to the third, all the way to the nth rectangle. So the k still represents the k as previously mentioned. The n still represents the number of rectangles we're using. F evaluated at x star is the height of each individual rectangle, and delta x is the length of all of them. The other important piece that we get is how do we actually define the x stars, the values of x that give us the height of each rectangle for the left, right, and midpoint Riemann sum. So for the left Riemann sum, the x value that we evaluate in the function is given by a, our starting value on this interval, plus k minus 1 delta x. The right Riemann sum, a plus k delta x, and the midpoint Riemann sum, a plus k minus a half times delta x. Notice where these x stars go. If we're using the midpoint, the right, or the left Riemann sum, we compute what these x stars are, and these things turn out to be, basically they're a function of k. They have that k inside them, or with them. But those functions of k have to go here. So we have to put these expressions a plus k minus 1 delta x, whatever that is, we have to then plug that into the function itself to get all of the heights as k goes from 1 to n, and then it's times delta x. So your process here in working with this definition is you first determine which one of these you're using that'll be given to you, but then you have to find these x star as some function of k. Then you've got to plug that function of k into your function, x squared, x cubed plus 5, whatever it is. And then that needs to go inside of the summation, or to be summed. So remember, this sigma operates on things that involve a k. This f of x star sub k is what you have to sum. No matter what that turns into, you have to keep all of the things that are produced there in front of the summation. The delta x doesn't involve a k, so this is a constant that can be pulled out of the summation. So another way we can look at this that might be helpful for computations is, at least for now, is the following. just gonna factor that constant, which is delta x, out, and then whatever is resulting from this x star sub k, you have to sum that. So maybe, I don't know, maybe view it like this. This thing has to get summed no matter what results. Because depending on the function, you could get like constants involved. Like if my function was like x squared plus 1, then I have to sum, the sum has to operate on the x squared part and the 1 itself. So let's put this in practice here and evaluate right, left, midpoint Riemann sums for x cubed plus 1 on the interval from 0 to 2 using 50 subintervals. So now we're getting into the realm where it's kind of impractical to start drawing things out. This stuff here in purple with the left-right Riemann, midpoint Riemann sums, how we define x star, that sort of eliminates the need to find all of the grid points. Because the reason we found were the grid points is because we needed to know which x value to plug into the function. Notice in how this is written, it already tells us what x value to plug into that function as an expression involving k. So I'm going to rewrite this. No matter which Riemann sum we're using, this is always the formula to calculate those. The only thing that changes by left-right Riemann sum is this x star, which gets plugged back into the function x cubed plus 1. Delta x is the same for all left, right, and midpoint Riemann sums. So since delta x is constant with all of these, part A, B, and C, let's go ahead and find delta x, and then we'll proceed from there. So really the first thing we need to do is find delta x. So what is our delta x?
It's 1/25, isn't it?
1 over 25, yeah, because it's the interval here. This is A, this is B. So B minus A over the number of subintervals, which is 50. So 2 over 50 is 1 over 25. All right. So for left, right, and midpoint Riemann sum, our delta x is 25. All right. So part A was the right Riemann sum, and for the right Riemann sum, our x star, all of our x stars were defined as what? As A,
F is k times the change in x.
yeah. So what's our A? 0. K is just k. This x star sub k will be a function or an expression involving k times our delta x, which is 1/25. So our x star sub k is k over 25. All right. Now these two pieces of information go into the definition. What do we need to do with the x star sub k according to the definition? Put it into the function. So I guess that's step 1. Step 2, we evaluate the function at x star sub k, because that's what's involved with the sum. our x star for the right Riemann sum was k over 25, and our function was x cubed plus 1. So our function is going to take this input, cube it, and add 1. Where are we at that? We were given that function was x cubed plus 1. So that's the x star, f of x star sub k that goes inside or in front of the summation times delta x. So really step 3 then is to just put that into the definition. We have our delta x, which was 1 over 25, times the sum from k equals 1 to n. What's our n? 50. So we're summing k equals 1 to 50. And then the expression in front of the summation was the f of x star. So our expression is this thing right here. You have to sum that. Even though this is a constant, this plus 1, it's part of the function, which means it's part of the summation. Okay, so maybe your calculator does some of these, maybe it doesn't. On D2L, I have a link to a summation calculator that you can use. So here's the summation calculator. We're going to type in our expression.
Only solve there by hand on the test one?
These won't be on the test. Once we get to the point where these things will be on the test, I'll point that out. But the one on the exam, final exam, will be an exact computation, not an approximation. So here's our expression involving whatever. Just make sure you specify your variable. So this is, we're using k, so our variable is k. The expression that we're summing is k over 25 cubed. So k over 25 cubed plus 1. And then our upper limit, we go from k equals 1 to 50. And then we're going to compute that sum somewhere. Okay, maybe keep it as n. Maybe it doesn't like k. I'm not sure. It was working earlier on the.
Is the lower limit 1 or is it 0?
1.
Okay, so
We go from 1 to 50. It's totally working just a minute ago. You should get a number right here instead of that.
Is it, do you have to multiply by a constant?
So well, yeah, I mean, whatever number we got there, we need to multiply by our delta x, but it should somehow spit out this decimal approximation. I'm not sure let's try this again. Yeah, over 25 cubed plus 1 to 50. Oh, there it is. Decimal form 154.04. And if your calculator does these, then probably now's a good time to figure out how it works. All right, so let's write our delta x here, and then the sum from the sum calculator for all of this stuff. What is it? 154.04. All right, times the 125th, give us 6.1616. That stuff is like secondary. We all need to make sure that we're okay with how we've constructed this. So are there any questions on the construction of this summation right here and how we obtained that? All right, so using 50 subintervals with the right Riemann sum on x cubed plus 1 from 0 to 2, approximate area is 6.16. So at least for this one, let me show you how it works if you're just doing it by hand and using all of those formulas. If you want to use the summation calculator, your calculator for the homework, that's totally fine. I just at least want to show you one example on where all the previous formulas come in. Well, let me just say here, summation calculator used. All right. So this will be, I guess, the long way. By hand. All right, so we have to sum k cubed over 25, or sorry, k over 25 cubed plus 1. And notice our formulas for the summation we have for the integers cubed and for a constant. So really what we're going to do is split this sum up so that it's just the sum of something times k cubed and then the sum of something times 1. So it will fit into those formulas. As far as the sum of a sum, we can look at distributing that summation across this plus sign here. This 1 over 25 cubed for this first term is a constant. It doesn't involve a k, so that gets pulled out of the summation. And then our next sum, the sum's distributed to 1, so it's just that. We have a formula for this sum and we have a formula for this sum. I don't know what it was called. Theorem 5.1. We have that 1 over 25 as our delta x times this 1 over 25 cubed. And according to the formula, the sum from k equals 1 to 50 of k cubed would turn into what?
N squared times 50 plus 1 squared divided by 4.
Right. So we have our n squared, 50 squared, times n plus 1 squared, all over 4. And then plus, what's the sum from 1 to 50 of 1? Yeah, it's just 50. So that's how we would do it by hand, and at this point we can type out that value. Do y'all have any questions on this? I mean, it's really involved, and a lot of this stuff we've done is really involved. I mean, maybe you can take some time to appreciate like all of the groundwork that was laid, so that this can be somewhat easier of a process, right? I don't know. It always amazes me to look at stuff like this and think people actually did this. People thought of this. People came up with this. They refined it. They proved all of it. You know, like it's, if nothing else, even if you don't like math, if nothing else, that's pretty amazing in and of itself. All right, so that's the right Riemann sum. Then we'll look at, for part B, the left Riemann sum. A reminder, the delta x we computed is the same for all of these, so that was 1 over 25. What changes from Riemann sum to Riemann sum is the x star sub k. So for the left Riemann sum, x star sub k is a plus quantity k minus 1 times delta x. So for us, the a is still 0. We've got a k minus 1 times our delta x, which is 1 over 25. All right, so that's our x star sub k for the left Riemann sum. Again, where does that go? What do we do with that? It goes into the function in front of the summation. So we've got our delta x times the sum, or well, rather, just keep it like we did the last one. We then computed the function evaluated at x star. So our function evaluated at this x star is all of this cubed plus 1. So to do this one by hand, our right Riemann sum just involved the k over 25 cubed. That was easy to cube. If we wanted to do this by hand, you have to expand this out, multiply this times itself 3 times, and then distribute the sum to all of those terms, factor out the constants, so it can get very, very tedious very, very quickly.
Would it not make sense to combine it with just k minus 1?
Say that again, combine.
The k minus 1 over the bottom. Make it one fraction.
K minus 1 over 25?
Can't do that.
Oh yeah, I mean this could be k minus 1 over 25. You still have to cube that though. But yeah, you can certainly make that inside the parentheses. Since we have a common denominator here, k minus 1 over 25. Yeah, that works. So the idea here is now this thing is what gets summed. So we've got to put that in front of the summation. That's our f of x star, and then we have our delta x out here. Remember, we're summing all of this stuff. So we plug that into the summation calculator to get 5.8416. Sorry, that goes from k equals 1 to 50 still. have any questions on that one? Okay. And then for the midpoint Riemann sum, delta x is 1/25. Our x star sub k is a plus k minus a half delta x. So we have k minus a half times 1/25. Or if you want to write that more compactly, it's k over 25 minus 1/50 is our x star. So that's the only thing that changes from different Riemann sums is the x star. In any case, the x star needs to be plugged into the function. And then that needs to be summed. So we have k over 25 minus 1/50 cubed plus 1. In front of the summation. So our delta x times the sum from 1 to 50 of all of this stuff. And that's our delta x sum. This is our f of x star. Should get that sum to come out to be 5.9992.
It's just an approximation.
Right, still an approximation, but it's a good approximation because we're using 50 subintervals. So the right Riemann sum gave us 6.1616. The left gave us 5.8416. The midpoint 5.9992. And the actual is 6. So that was x cubed plus 1, so it kind of looks like this, from 0 to 2. And that area, exact area is 6. I know break's coming up, you probably don't want to do math during break, but it would be advisable at least to look at some of this stuff, so that way when you come back, it's not just totally gone. All right, I hope you all have an awesome break, well deserved. Get some rest, take it easy.